The purpose of this video is to review our differentiation rules by working through several examples. In this problem, we want to differentiate the function f of t equals 5 times the square root of t minus t to the fifth, all divided by t squared. One way you could approach this problem is to use the quotient rule. However, because the quotient rule is rather messy, it's best to avoid that if you can. So we can use some algebra, split up this fraction, write it as 5 times the square root of t divided by t squared minus t to the fifth divided by t squared. And then, remember, the square root of t is t to the 1/2. And so we can use our rules of exponents to write our function as 5 times t to the negative 3/2 minus t to the third. Now I can take the derivative, f prime of t, just by using the power rule. So I have 5 times the derivative of t to the negative 3/2 is negative 3/2 t to the negative 5/2 minus the derivative of t to the third is 3t squared, which overall gives us negative 15/2 t to the negative 5/2 minus 3t squared. In this problem, we want to find an equation of the tangent line to the curve at the given point. Our curve is y equals x times 2 to the x, and our point is 1, 2. We know that the equation of a line is given by y minus y1 equals m times x minus x1, where x1, y1 is any point on the line and m is the slope. Now we know a point on this line is 1, 2. So x1 is 1, y1 is 2. The slope of a tangent line is the derivative at that point. So the slope that we need is the derivative dy dx evaluated at the x value 1. So let's find the derivative. Because we have these two functions multiplied, we know that we need to use the product rule for derivatives. The product rule says we take the first function, we multiply by the derivative of the second function, and then we take the second function, we multiply by the derivative of the first function, and we add those terms together. So we have x times the derivative of 2 to the x is 2 to the x, natural log 2, plus 2 to the x, and the derivative of x is 1. And so the slope of our line is what I get when I plug in 1 for x. 1 times 2 to the 1, natural log 2, plus 2 to the 1 times 1, which is 2 natural log 2 plus 2. Now I'm ready to write down the equation of the tangent line. We have y minus 2 equals the slope 2 natural log 2 plus 2 times x minus 1. Distributing the slope on the right side, we have 2 natural log 2 plus 2x minus 2 natural log 2 minus 2. And adding 2 to both sides, we get y equals 2 natural log 2 plus 2 times x minus 2 natural log 2. This is the equation of our tangent line. In this problem, we want to differentiate the function a equals secant of r divided by 1 minus r. Because my function is named a and my independent variable is r, we will call the derivative dA dr. I also see that I have a fraction, secant r divided by 1 minus r. This tells me that I will need to use the quotient rule for derivatives. The quotient rule says I take the bottom and I multiply by the derivative of the top, Then I subtract the top multiplied by the derivative of the bottom, and I divide all of that by the bottom squared. Taking those derivatives, I get 1 minus r times the derivative of secant r is secant r times tangent r minus secant r times the derivative of 1 minus r is negative 1. All of this divided by 1 minus r squared. Cleaning up a little bit, we have 1 minus r times secant r tangent r plus secant r, all divided by 1 minus r squared. For most purposes, this expression is going to be perfectly fine. If you wanted, you could factor out a factor of secant r, and you could distribute the tangent r, write tangent r minus r times tangent r plus 1, all divided by 1 minus r squared. This expression is perfectly fine. Our last example is to differentiate the function g of x equals arctangent of 1 divided by e to the x minus the cube root of x. Again, I'm first going to spend just a moment rewriting our function g of x. Remember, the cube root of x is x to the 1/3, and 1 divided by an expression is that expression to the negative 1 power. So our function can be rewritten as arctangent, or in other words, tangent inverse of e to the x minus x to the 1/3, all to the negative 1 power. Now I observe that I have functions nested inside of one another. That means I need to use the chain rule. The chain rule says that you take the derivative of a composition of functions by taking the derivative of the outermost function with respect to the inside and multiplying by the derivative of the inside. Our outermost function is tangent inverse, and I know that the derivative of tangent inverse is 1 divided by 1 plus the inside squared. The inside currently is e to the x minus x to the 1/3 to the negative 1 power. And then the chain rule says that I multiply that by the derivative of the inside, which is e to the x minus x to the 1/3 to the negative 1 power. Now, in the derivative that remains, the outermost function is a base raised to the negative 1 power. So I'm rewriting this fraction, 1 over 1 plus e to the x minus x to the 1/3 to the negative 2 power. And I'm multiplying by the derivative of a base raised to the negative 1 power, which by the power rule is negative 1 times that base raised to the negative 2 power. And then I multiply again by the derivative of the base, e to the x minus x to the 1/3. Rewriting the initial part of our expression, multiplying fractions, we have negative 1 times e to the x minus x to the 1/3 to the negative 2, divided by 1 plus e to the x minus x to the 1/3 to the negative 2, and multiplying by the derivative of e to the x minus x to the 1/3, we multiply by e to the x minus 1/3 x to the negative 2/3. This expression is fine. You could clean this fraction up a bit by multiplying the top by e to the x minus x to the 1/3 squared, and also the bottom by e to the x minus x to the 1/3 squared, which would give you a slightly neater expression of negative 1 divided by e to the x minus x to the 1/3 squared plus 1 times e to the x minus 1/3 x to the negative 2/3.